Today, we're going to be discussing 3 of the most common properties, or perhaps I should say types, of probability situations which may occur. So first, I'm going to write down just the name of it along with the mathematical definition, and then we'll discuss what they actually mean. I'll give you some examples of things where these could occur. So the first most common type of probability is conditional. And so this would be read as the probability of A given B, if you see this notation. Now, this is actually equal to the probability of A and B over the probability of B. So, what is conditional probability? It's probability that something happens given you have other information. So, for example, say we have the probability that it rains given that it's humid outside, or something like that. Knowing that it's really humid outside intuitively seems like it'd be more likely to rain. So then if you look at this, it says that's the probability that it rains and it's humid divided by the probability that it's humid. So you're taking all the cases that overlap, that have both of what you're talking about, and dividing them by your sample space is this thing that you already know. So it's like you're dividing out the probability that this happens because you already know it did. It's humid outside. We'll do more examples when I start mixing this with the other 2 possible conditions or types of probability. So another thing that may happen is that you may have mutually exclusive events. What does this mean? Well, first of all, here's the mathematical definition. If 2 events are mutually exclusive, so the probability of A and B, that means that this probability right here is going to be 0. So it means that 2 events cannot happen at the same time. The probability of A and B occurring is 0. That doesn't mean that the probability of either one is impossible, just that they can't happen together. So for example, say the probability that I grab a random sock and it's blue versus the probability that I grab a random sock and it's red. Again, assuming I have monochrome socks that are just one color and I don't have multicolored socks. Then that means that there's some probability I grab a blue one, there's some probability I grab a red one, but the probability that for one sock I grab that it's both red and blue, the probability of that would be 0, again, assuming I don't own any socks that are multicolored. A more easy to think of example is say that you roll a die. What's the probability that you roll a 1? Well, that's 1 out of 6. Probability I roll a 5, that's 1 out of 6. Okay, cool. But what about the probability that on that one roll, I roll a 1 and a 5? It doesn't make any sense, right? Like on a die, you either get one number or a different number. You can't get both. So those events would be mutually exclusive. And that's supposed to be a U, if you can read my handwriting. So, the third thing is you could have events which are independent. Well, the mathematical definition of this is that the probability of A and B is equal to the probability of A multiplied by the probability of B. So that means that the probability that one event occurs is not affected by the probability of another event occurring. So to take the dice example, say I roll 2 dice. So let's say the probability of A is that I roll a 1, and the probability of B is that I roll a 5, and I don't care which die it's on. Well, then in that case, you've got the probability that one of these dice is a 1 multiplied by the probability that one of these dice is a 5. Now, because I'm not talking about one dice having both numbers, I'm just saying that one thing happens and another thing happens. These would be independent events because what I get for the first die has no effect on what I get for the second die. You could also think of it as rolling a dice twice back to back. I roll a die one time and then I roll a die again. And so if I want to know the probability that I roll a 1 the first time, that's just a 6th. Then when I go to figure out the probability that I roll a 5 the second time, that's not going to change. Like what I got the first time has no effect on what I got the second time. And so I would just multiply these probabilities together. So those are the 3 most common terms that you want to be familiar with. Now, let's talk about what happens when I mix these things together. So let's say we had something. First of all, I'll give numbers to each of these. So let's just say this is my first definition, this is my second definition, and this is my third. Let's talk about what happens when I mix these together. So first, let's say I had something that was conditional but multiply exclusive, and just see what that means. So we've got 1 and 2. Well, first of all, let's just do the math. We know that the probability of A given B is equal to this guy right here, probability of A intersect B over the probability of B. But we also know that the probability of A intersect B is 0. So this is 0 over the probability of B, which that's just 0. Well, that's kind of strange. So we've got the probability that A happens given that B happens comes out to be 0. Let's try to interpret what that means. So let's say you had a statement like, what's the probability? Here's a good one. Let's say A is the case that 2 is greater than 3. Well now, regardless of what B is, as long as it's possible, remember because you can't divide by 0, so we want the probability of B to be some number. Let's say B is that, I don't know, I eat a sandwich. Just say my brain is just some random processes and I just randomly decide what to eat today. There's a probability I'll pick a sandwich, right? So then we have the probability that 2 is greater than 3 given that I eat a sandwich. Well, think about what this says. It should sound really silly. We're saying I eat a sandwich, that could happen, so I know I ate a sandwich. Now, given that I ate a sandwich, what's the probability that 2 is greater than 3? Well, it's still 0, right? Because there's no way that can happen. Now, this is if I have something that's totally silly and can't happen at all. But really, mutually exclusive is that A and B can't happen together. So now, let's get rid of this silly condition. Let's say that A is that for the same meal on that day, and let's just say my stomach's not this big, even though it is. Let's say I eat a burrito, right? Or I just don't have the money to buy both. Well, now what happens is that given that I ate a sandwich, you know that I can't eat a burrito as well because it was one or the other. So they're mutually exclusive events because I can't buy both. So when you do the conditional probability, it just comes out to be 0. So the focus here is on understanding what does this mean. You can do the math, you can get that just equals 0 and go home, but it's helpful to interpret what's going on here. Okay, let's mix something else together. Let's say we mix 1 and 3, so conditional and independent. So now, let's use the dice example. Let's say that A is, for 2 dice rolled back to back, I roll a 2, and let B be, I roll a 1 on a regular die. So now we're going to say the probability of A given B. And we know that's equal to the probability of A intersect B over the probability of B. So we're asking, what's the probability I roll a 2 given that I already rolled a 1? Well, we know these are independent, right? So we know that the probability that I roll a 2 and then a 1 is just equal to the probability that I roll a 2 multiplied by the probability I roll a 1. So let's throw that in here. Probability I roll a 2 multiplied by the probability I roll a 1 over the probability I roll a 1. Notice that mathematically these match, right? So they cross out. And we just get the probability of A, which is the same thing as just the probability I roll a 2. Well, let's think about that. If they're independent, then one event happening has no effect on the other one, right? Saying whatever I roll for my first roll has no effect on what I'm going to roll for my second roll. So if it has no effect, and you read off the conditional stuff, this is saying that what's the probability that I roll a 2 given that I already rolled a 1? Well, basically what we're saying is that it doesn't matter. Knowing what I've already rolled should have no effect on how likely I am to roll something now. And if you go through the definition, that's exactly what we get. It's just equal to the probability that I roll a 2. So if you've got a conditional probability, but you know that the events are independent, then basically the conditional thing doesn't tell you anything. You just know that it's the same probability either way. So let's mix one more thing. Let's mix 2 and 3, mutually exclusive and independent. Okay, well this is interesting because if they're mutually exclusive, then we know that the probability that A happens and B happens is 0. But if they're independent, we also know that the probability that A happens and B happens should also equal the probability of A times the probability of B. Well, what does that mean? First of all, we get that this means that probability of A and B occurring together is impossible. It's 0. But if we look over here, we've got two things getting multiplied together. So that would mean that either this probability is 0 or this probability is 0, or perhaps both. That's interesting. Well, let's go back to this example I had before. Let's say that A is the probability that 2 is greater than 3. And let B just be the probability, I don't know, on a die that I roll a 2. Well then, first of all, the probability of A and B happening together is 0. And it doesn't so much have to do with the fact that these can't happen at the same time, but more so with the fact that A just can't happen at all. 2's not bigger than 3. So the probability that that just randomly is bigger than 3, it's not going to happen. It's just not true. So now if you look over here, what happens is we've got a probability of 0 multiplied by a probability of 1/6, which just comes out to be 0. So what's going on is just you've got something that can't happen multiplied by the possibility of something else happened. And so you still just get nothing at all. So it is possible for something to be mutually exclusive and independent, but basically what that means is that one or both of those things are impossible in order for that to happen. Because we know independent means you just multiply their probabilities, but if we know that comes out to be 0, one of these guys has to be 0, and in terms of probability, having a probability of 0 means that it's impossible. So those are 3 of the most common terms for probability that you want to be comfortable with, along with their mathematical definitions. And these are some of the ways to mix them. Of course, you can mix these in other ways. I didn't do some of these other possible mixings because it doesn't really make much sense to do so. Plus, notice that because conditional probability has division by the probability of B, I have to be really careful that that guy's never 0, because then we get a division by 0 error. In other words, conditional probability just doesn't make sense for some of these types of mixings. So that's a general overview. My main focus is just be comfortable with these formula and always, always interpret what your results mean. What must be going on to get these results that we're getting? Make sure to always do that for any of your classes. It's a very useful skill to analyze. And that is this overview.